Welcome to our exploration of angular kinematics and human movement. In this lecture, we'll dive into the fascinating relationship between angular and linear acceleration. Understanding these concepts is crucial for fields like biomechanics, sports science, and physical therapy. Today, we'll break down how angular motion translates into linear motion and why this matters for analyzing human movement. Whether you're a student, athlete, or just curious about how our bodies move, this journey will help you see motion from a new perspective. Let's begin by setting the stage for the key concepts we'll cover. Before we dive into their relationship, let's clarify what we mean by angular and linear acceleration. Angular acceleration refers to how quickly an object changes its rotational speed, while linear acceleration is about how quickly its velocity changes in a straight line. In biomechanics, both types of acceleration play a role in understanding how limbs and joints move. For example, when you swing your arm, your shoulder experiences angular acceleration and your hand experiences linear acceleration. These two forms of acceleration are interconnected, and understanding them helps us analyze complex movements. What is the relationship between linear and angular accelerations? When a body moves in angular motion, its acceleration can actually be split into two perpendicular linear components. This means that even though a joint or limb is rotating, parts of it are also accelerating in straight lines. This dual nature is fundamental to understanding how rotational movements translate into real-world actions, like throwing a ball or swinging a bat. By resolving angular acceleration into linear components, we can better predict and analyze movement outcomes. Help visualize this. Imagine a rotating arm. The acceleration at any point on the arm can be broken down into two directions, one along the tangent of the motion path and one pointing toward the center of rotation. These two components are known as tangential and radial acceleration. By understanding these directions, we can see how complex rotational movements are actually made up of simpler linear accelerations working together. Let's focus first on tangential acceleration. This component is directed along a tangent to the path of motion. In simple terms, it represents how quickly the speed of a point on a rotating body is changing. For example, when you spin a wheel faster, the points on its edge experience greater tangential acceleration. In human movement, this is like the increase in speed of your hand as you swing your arm faster. Tangential acceleration is crucial for understanding how we generate speed in rotational movements. Now let's look at radial acceleration. This component always points toward the center of curvature of the motion path. Radial acceleration is responsible for changing the direction of the moving point rather than its speed. Think of swinging a ball on a string. The string pulls the ball inward, creating radial acceleration. In human movement, this helps us understand how joints guide the direction of our limbs during rotation. Both tangential and radial accelerations work together to create smooth, controlled motion. In analyzing angular motion, it's important to remember that tangential and radial accelerations are perpendicular to each other. Together, they form the total linear acceleration experienced by a point on a rotating body. This combination allows us to fully describe the motion, predict outcomes, and design better training or rehabilitation programs. By breaking down acceleration into these components, we gain a clearer picture of how complex movements are coordinated. Let's apply these concepts to a real-world scenario. A baseball pitcher's arm. When a pitcher throws a ball, their arm rotates about the shoulder joint with a certain angular acceleration. The distance from the shoulder to the hand is important because it determines the linear acceleration of the hand. By knowing the angular acceleration and the radius distance from the joint, we can calculate how quickly the hand accelerates in a straight line, which directly affects the speed of the pitch. Suppose a pitcher's arm rotates with an angular acceleration of 50 radians per second squared, and the distance from the shoulder to the hand is 0.7 meters. To find the linear tangential acceleration of the hand, we multiply the angular acceleration by the radius. This calculation helps us understand how changes in joint movement translate into the speed of the hand, which is critical for performance in sports like baseball. Here's a visual representation of the pitcher's arm in motion. Notice how the hand traces a circular path around the shoulder joint. The linear acceleration of the hand is always tangent to this path, while the radial acceleration points inward toward the shoulder. This visualization helps us see how the two components work together to create the overall motion of the arm during a pitch. Let's look at another example, a boat traveling around a circular path with a radius of 40 meters. The boat's speed increases over time, following the equation v equals 0.0625 t 2 meters per second. At a specific instant, say t equals 10 seconds, we can calculate both the velocity and the acceleration of the boat. This example shows how the same principles of angular and linear acceleration apply to different contexts, not just human movement. First, let's calculate the velocity of the boat at t equals 10 seconds. Using the given equation v equals 0.0625 times 10^2, we find that the velocity is 6.25 meters per second. This step is crucial because both tangential and radial accelerations depend on the velocity of the moving object. Knowing the velocity allows us to move on to the next step, finding the acceleration component. Next, we calculate the tangential acceleration. This is found by taking the derivative of the velocity equation with respect to time. In this case, the tangential acceleration at t equals 10 seconds is 1.25 meters per second squared. This value tells us how quickly the boat's speed is increasing along its circular path. Tangential acceleration is always directed along the tangent to the path, just like in our earlier human movement example. Now let's find the radial or normal acceleration. This is calculated using the formula n equals v2/radius. Plugging in our values, we get n equals 6.25/2/40, which equals approximately 0.98 meters per second squared. Radial acceleration always points toward the center of the circle and is responsible for changing the direction of the boat's velocity as it moves along the circular path. find the total acceleration, we combine the tangential and radial components using the Pythagorean theorem. In this example, the total acceleration at t equals 10 seconds is about 1.59 meters per second squared. This value represents the overall rate at which the boat's velocity is changing, both in speed and direction. Understanding total acceleration is essential for predicting motion in any rotating system. Here's a diagram showing the boat's motion along the circular path. The velocity vector is tangent to the path, while the acceleration vector is a combination of tangential and radial components. This visualization helps us see how the boat's movement is governed by the same principles we discussed for human movement, highlighting the universality of these concepts in physics and biomechanics. Summarize what we've learned so far. Angular acceleration describes how quickly something rotates, while linear acceleration describes how quickly it moves in a straight line. In rotational motion, linear acceleration can be split into tangential and radial components. These principles apply to both human movement and objects like boats or wheels. By understanding these relationships, we can better analyze and predict motion in a variety of settings. Biomechanics, these concepts help us understand how athletes generate speed, how injuries occur, and how to design effective rehabilitation programs. For example, knowing the relationship between angular and linear acceleration can help coaches improve a pitcher's throwing technique or help therapists design exercises that safely increase joint mobility. The practical applications are vast and impactful. One common misconception is that linear and angular accelerations are completely separate. In reality, they are deeply connected, especially in rotational movements. Another misconception is that only the rotating joint matters, but the distance from the joint, the radius, plays a crucial role in determining linear acceleration. Understanding these nuances helps avoid errors in analysis and application. Reinforce your understanding. Try applying these concepts to other examples like a spinning wheel or a swinging pendulum. Calculate the tangential and radial accelerations and see how they combine to create the total acceleration. Practicing with different scenarios will deepen your grasp of these fundamental relationships and prepare you for more advanced studies in biomechanics or physics. Conclusion: the relationship between angular and linear acceleration is a cornerstone of understanding motion in both human bodies and mechanical systems. By breaking down acceleration into tangential and radial components, we gain powerful tools for analysis and application. As you continue your studies, keep these principles in mind. They will serve as a foundation for more complex topics in biomechanics, engineering, and beyond.